Professor Dr. N. Ganesh is working as a senior faculty, Department of Computer Science and Engineering, SRM University, City Campus, Vadapalani, Chennai. He has more than 12 years of undergraduate and postgraduate teaching experience, which includes 5 years of research experience. He has trained many corporate batches on technologies such as mainframes, Application Systems 400, SAP, ABAP. He has published 10 articles in both international and national journals. He has presented several papers in both national and international conferences. He has written 4 books which are prescribed in Anna University affiliated colleges, SRM University and Bharat University. His research interests are software engineering, data mining and cloud computing.
Welcome to UGC lecture series in computer science. We are going to see a series of lectures in the subject operating systems. This subject is for the students studying in the 5th semester of their BSc degree program. This operating system belongs to paper number 8, in which in today's session we are going to see few topics from unit 2. So in unit 2 we have many different topics, out of which we are going to see a topic on process synchronization, and then we have already seen topics on what a process is and how a processor gets executed. In today's session we will be seeing topics on process synchronization and then about critical session problem and how to handle the critical session problem and what are the solutions for handling a critical session problem and how hardware gets synchronized for this kind of critical section problem. So these are things which we are going to see in this session. Now today's topic is on process synchronization. So these are the contents. First content is critical section. We will be seeing what a critical section is. We have already seen in a previous lecture about what a process is or how a process gets executed. What is a process? So we have seen a process is a program in execution. So in today's class, in today's session, we will be seeing this program in execution when it goes into a critical session, how it gets handled. So that will be the first content. The second content is we will be seeing the solutions for handling the critical section. That is, supposing if the process goes into a critical session, how to handle or what sort of measures to be taken in order to take the process out of a critical session. So if it has been into a critical session, how to make the process to come out from the critical session. And then the third content is about the synchronization hardware. So what is a synchronization hardware? If the process gets into a critical section, then how the hardware of a particular computer system helps the software. That is, how the hardware helps the process to come out of the critical section is what we are going to see, and how this software, this process gets synchronized with the hardware and how it makes the process to come out of the critical section is what we are going to see as the third part in this session. Now, what is a thread? What is the difference between process and thread? All these details we have already seen in our earlier lectures. But to give a recap, what a process is? A process is a program in execution. What is a thread? A thread is a line of execution. It is a single line of execution. Then what is a multiprocess? A multiprocess is 2 or more number of processes gets executed at a single instance of time. You call it as multiprocess. What is a multi-threading? 2 or more number of threads, that is 2 or more number of lines of code gets executed at a same instance of time. You call it as a multi-threading. Then what is a multitasking? 2 or more number of tasks gets executed at the same instance of time. You call it as multitasking. Now, how to handle these situations. When two or more number of tasks gets executed, or when two or more number of threads gets executed in the case of multi-threading, or when two or more number of processes gets executed in the case of multiprocessing, then definitely before entering into a deadlock state, it has to go to a critical session, then only it will go to a deadlock state. Now, how to overcome this situation? That is what we are going to see. Now, as I said, what is a deadlock? This deadlock concept we have seen in one of our earlier sessions. So, again I will give you a recap on what a deadlock is. A deadlock is a situation wherein two or more number of processes is waiting for a single resource that both these processes request on. Supposing if there are two processes, one process requires this printer resource to get printed, and the second process, say for example P2, it also requires this printer resource. Then if both these processes ask for the printer resource at a single instance of time, then, and supposing if the printer resource has been occupied by the other process called process P3, then process P1 and P2 has to wait in queue until process P3 releases that printer resource. Then if the process P3 is not at all releasing the printer resource for quite a longer time, then process P1 and P2 may get into a deadlock. I explained this with an real-time example, even with a traffic jam example that you could encounter on a day-to-day basis. Supposing if two cars or if two buses come in the opposite direction and if they stand head-on towards each other, then none of the bus or none of the car could move from one place to the other. Supposing if it is of a single way, and if two cars, if one car comes from left to right, and if the other car goes from right to left, and if both the cars meet at a point wherein for both the cars it will not be in a position to move until either of one of the car moves out. That is called as a deadlock. So why I am giving such recaps is, for conducting this session you require all these recaps. One is about the process. You are supposed to know what a process is. You are supposed to know how a process gets executed, how the programs gets executed, what a thread does, how the threads are getting executed, what are the prerequisites for a process execution, something like stacks, something like the parameters of passing, something like the temporary variable declarations, something like the PCBs, and then you are supposed to know what a deadlock is. Now, I said about PCBs. What is a PCB? A PCB is a process control block. What does a process control block has? It contains the data about, the information about the entire process. So, that gets stored in the process control block. As well, you are supposed to know the different states of the processes. What are the different states of processes that you have seen in an earlier lecture? There were several states, like one is a new state, other one is a ready state, third is a waiting state, fourth is a running state, fifth is a termination state. In a new state, a new process has been created. In the ready state, the process gets ready for its execution. When the process gets ready, where will it get stored? I suppose you could remember from a previous session that all these processes gets executed, or when it is in the ready state, it will be placed in the main memory before it gets executed. So, then the third state is said to be a running state, wherein the process gets executed. Then, supposing if a higher priority process comes in and if it's going to stop this process execution, then this process has to be put on hold and the process will get interrupted. Such a state you call it as a waiting state. Then what is a termination state? Supposing the process has completed its execution, finishes its execution, then it goes to a process termination state. Now with this, supposing in our fourth state, if it has been put on hold, if a higher priority process comes in and two or more number of processes which has more priority than this process wanted to execute, then this process will be put on hold. Then this process will be waiting. A process which has been put on hold will be waiting till the higher priority process occupies the resource until the higher priority process frees out the resources. Then before this process which is under waiting, before it goes to a deadlock state, it enters into a critical section because of all the concurrent processes that has been going on. So what is a critical section? So if it is going to enter into a critical section, how it has been handled? Here it is what will happen to a data. First we will see what will happen to the data that has been put in a process. Here the concurrent accesses to share data may result in data inconsistency, because at the same time you are going to access the data which has been shared and it will result in inconsistency. Then maintaining data consistency requires mechanism to ensure the orderly execution of cooperating process. I suppose you might be remembering the details of a cooperating process, the difference between a cooperating process and an independent process. Two or more number of processes, if it is going to share a particular data and if it is going to work, then these two processes will be cooperating together. I suppose I gave you an example even with respect to a mutual exclusion, with respect to a cage example in one of my sessions. Now, here we will see what a critical section is. A critical section problem is to design a protocol in order to solve the entry of critical section. Each process must ask permission to enter critical section in the entry section and may follow critical section with exit section, then the remainder section. In a critical section, there are three different sections. One is called the entry section, the final section or the termination section you call it as an exit section, and after exiting also there may be certain things which may be put on hold for a certain period of time. That is called as a remainder section. So there are three different sections. One is entry section, second one is the exit section, and third one is the remainder section after it gets exited out. Then we will consider a real-time example with a process and then we will see how it works on a critical section. Here consider a system of n processes wherein you have P0 as to be one process, P1 is the other process, etc. up to Pn minus 1. Each process has a critical section of code. Process may be changing the common variables, updating table, writing files, etc. When one process is in critical section, no other process will get into a critical section, and it is challenging with respect to preemptive kernels. I suppose you might be knowing what a kernel is, what a preemption is. So I am not going to give more explanation on preemption and kernel because we have seen much about it in our earlier session. So kernel is something like a nucleus of an operating system, which will be a core part of an operating system. Then here in this case, in preemption, in this critical section, wherein since the critical section occurs only because of sharing of data, mainly because of sharing of data. So when the data has been shared, then definitely it goes on to a critical section. And when this process goes into a critical section, the thing is at a single instance of time, only one process can go into a critical section, wherein the other process has to be put on hold. Until this process comes out from the critical section only, the next process will go into a critical section. So let us see a code snippet. I said, what is a code snippet? A code snippet is a part of code. Here it is do, entry section, and then critical section, exit section, and remainder section, and while. So we will see more about this diagram after the break. Welcome back after the break. Now, in our earlier session, that is before the break, we were speaking about a critical section. So, how a critical section occurs? A critical section occurs mainly because of sharing of data. If multiple processors wanted to share a single data, then a critical section occurs. And we also saw how many processes could occupy this critical section. At a time, at a single instance of time, only one process could occupy this critical section. We as well saw what are the three different sections inside a critical section. One is an entry section, other one is an exit section, third one is a remainder section. So, now we will see on a program code snippet. In this code snippet, wherein this is said to be a general structure of process Pi, where you can give as many processes as you want. Here, do entry section, critical section, exit section, remainder section, while of true. So, this example has been taken from one other book, and that is why it has been given as figure 6.1. So, here in this entry section, this process Pi, if say for example, if I am going to have 10 different processes, what will happen is, it will be going into this critical section only on a one by one basis. So, this P1, if there are 10 processes, then first process enters into a critical section where it is called as an entry section, wherein it has to undergo a critical section, then it exits from that area. And before exiting, if it is going to hold certain resources, then again those things will be put under a remainder section. Then the second process gets in, then the third process gets in. So, until all the processes gets in and exits out, this loop continues. So, that is a structure of process Pi which gets entered into a critical section and which comes out of a critical section. Now, we will see certain solutions for solving this critical section problem. There are three different solutions. Solution number one is the mutual exclusion. What is a mutual exclusion? If process Pi is executing in its critical section, then no other process can get executed. So, till this Pi comes out of the critical section, P1 comes out of the critical section, either P2 or P3 or P4 or whatever process waiting, it should be waiting. It cannot come out. Then, if the other process, then if process P2 enters in, then which means that P1 has exited from the critical section problem. So, when P2 enters in, P3, P4, P5 has to wait and queue till this P2 comes out of the critical section. So, that is one, mutual exclusion. I suppose you have seen a similar kind of mutual exclusion topic when we saw a topic on deadlocks. So, this mutual exclusion is also holds a similar meaning with respect to the deadlock meaning. Then, the second solution is progress. If no process is executing in its critical section and there exists some processes that wish to enter the critical section, then the selection of processes that will enter the critical section next cannot be postponed indefinitely. What does this mean? Here, we have, supposing if the critical section has been put free, if it has been left free, we have four different processes to enter into a critical section and which should come out of a critical section. In this case, supposing if this critical section is free, out of these four processes, it does not mandatory that the process which has been put at the first should enter first. But that is the normal rule. But there are exceptions. In the case of a high priority process which is waiting for a pretty longer time, and if it has been placed at the second level or the third level, even that can enter inside. So, that is the progress. So, it is based on the priority value even, and it cannot access like the next command, and the other processes which is waiting in the queue, it cannot made to wait for an indefinite period. So it can wait only for a definite amount of period, and if the section is free, then definitely it has to enter into the section and it has to come out of the section. So that will be the second solution to handle a critical section. The third solution is bounded wait. What is a bounded wait? A bounded wait, a bound must exist on the number of times that other processes are allowed to enter their critical section. After a process has made a request to enter its critical section and before that request is granted. Assume that each process executes at a non-zero speed, no assumption concerning relative speed of the n processes. Here it is a bound must exist on the number of times that other processes are allowed to enter their critical section. So there should be a definite amount of time in order to get completed when it goes to a critical section. So how it determines, how does it go out, will be carried out only with respect to a bounded wait. Bounded is nothing but anyhow the process is going to wait. So how many instants of time or how long that particular process has to wait, that will be determined by the operating system. So that kind of waiting, so if it knows this process will be waiting for some 5 milliseconds, then the other process which is P2, which can wait for only for 2 milliseconds, which may be a higher priority process. This other process which may be waiting for 7 milliseconds. So what happens is that this P2 will go into a critical section and it gets completed out. Then P1 goes into a critical section, then it exits out. Then P3 goes into a critical section and it exits out. So this is one other solution. So we have seen 3 different solutions. One is a mutual exclusion. Second one is based on the progress of the process. That is, if the section is fully free, the other processes which is waiting to enter the critical section cannot be put on an indefinite wait. It has to enter at one particular moment. Third one is the bounded wait. If at all it goes in, it has to have a bounded value of time and then it has to get bounded with the other processes even. So these are the 3 different solutions for a critical section problem. Now let us see how this critical section is being supported by the hardwares that we use. In most of the computer, what do you mean by hardware? There is a difference between a software and a hardware. A software is one which we are installing it. A hardware is one which is like your entire CPU. We call it as a hardware, wherein you have your hard disk, you have your main memory, you have your motherboard, you have other things. Here, how that hardware helps this software to complete or to complete this critical section. So, and many of the hardware, it is not that all hardwares help the softwares, all hardwares help the critical section problem. It is most of the hardwares present will be helping the critical section problem. How does it help? In terms of having interrupts. What do you mean by interrupt? Interrupt is, supposing if a process gets executed and if other process comes in, then this process may get interrupted because of its priority that has in the other process. So this interrupt, it can either be a software interrupt or it can be a hardware interrupt. I suppose you would have known about the hardware interrupts when you were handled or when you have studied the topic with respect to microprocessors. So in the subject microprocessor, we would have seen the difference between software interrupt and hardware interrupt. So here even this softwares in which the processors are there, this process, if it enters into a critical section, it gets help from the hardware element. based on the interrupt that we get from the hardware, this process which is inside the critical section will come out. So, we will see the different ways of entering different hardware that helps this critical section problem to solve. One is about a uniprocessor. Here even we have a point to note, many systems provide hardware support. Again, as I said, it is not all the systems. One is the uniprocessors. The uniprocessor that could disable interrupts. A uniprocessor is one which works with a single processor. Wherein, if you are going to say Pentium 1, Pentium 2, Pentium 3, Pentium 3 is a single processor. So, which works with a single processor is called as a uniprocessor. So, when you are going to work with the uniprocessor, it disables the interrupt. As well, the process gets, the process comes out of the critical section, which helps the process to come out of the critical section. Then, the points over here are, in the uniprocess, currently running code would execute without preemption. Second point is, generally too inefficient on multiprocessor system. That is, operating systems using this are not broadly scalable. So, what do you mean by preemption? A preemption is, supposing if anyone comes in, I gave you a real-time example in one of my other session. Supposing if anyone comes in, you get interrupted and you answer the query for the newcomer who enters in, and until that newcomer moves out of the classroom or anywhere you meet him, you will not be carrying out with the task, with your task. That is called preemption. No preemption is, supposing if you are handling a task and supposing, consider if a new entry, if a new person enters inside your classroom, and even without bothering that new person's entry, if you are going to carry out your own work, your own classroom work, and after completing your task, if you are going to pose question on the newcomer about a late entry or so, that is called no preemption. So, here this hardware synchronization, what it does is, it currently runs code for executing without preemption. And then, this operating system, if it is being used for a multiprocessor system, it is not fully scalable. Now, let us summarize whatever we have seen in this session. We have learnt about what is a critical section, how data or how concurrent data enters inside a critical section. We have as well seen certain solutions for critical section. We have seen how the hardware system helps in solving the critical section issues. We have as well learnt certain details about how the hardware gets synchronized with the software or with the process that is being placed inside a critical section. Now, let us see the possible questions that could arise from this session. Question number 1 is, what is a critical section? Question number 2, what is an entry section? Question number 3, what is an exit section? Question number 4, what are the possible solutions to overcome the critical section problem? Question number 5, what is a bounded wait? Question number 6, how interrupts help critical section code exclusively in the uniprocessor system. So, with this, we come to the end of the session. Thank you.